everyone. If you didn't see my video, Viviani's down volume, over here you can see a little sketch. Hello everyone, this is Kim. This time I'm going to find the Viviani's down volume using Monte Carlo Simulation. So this is the second part of a video. My first video was entitled Finding Viviani's down volume, part 1. I will put the link below my video just to follow the formulas, because I will be straightforward. So I will use 1 million points. I will sample 1 million points. The density will be unitary, because with this integral you can both calculate volumes and weights also. This time we are interested in only in volumes. So what we have to do is create well, two things. First of all, our volume of reference will be a sphere, the sphere centered in the first and second quadrant, right? So in the first and second quadrant, the volume of a unitary radius, I have to say it, is 1.04719 cubic units of measure, right? So after this, what I'm going to do is creating a loop in which we are moving from j being 1 to 1 million points. So we have to sample all of these points. Let's create it simply, well, if you want main loop, we can call it simply just going from j being 1 to nt total number of points, which is 1 million. What I'm going is just to finish the loop, just in case, to avoid errors. Now I'm going to initialize the variables x, y, and z with value of 1. What I'm going to do this because I need a filter, a while filter. I need to make sure that the points are inside a sphere, a unitary sphere, centered in the 0, 0, 0 coordinates. So I want to make sure that if our initial point for whatever reason is outside the unitary radius, what I'm going to do is using randomly with uniform distribution, I'm going to find these values. So this is why I use the command uniform between -1 and -19, no, -1 and 1 this time, because the cylinder moves in the positive and the negative axis of x, and just simple the function rand, values between 0 and 1 for y, and for z also the same. So if our point is larger than 1, I need to do this while end loop till the condition is satisfied. In fact, till this position is inside the unitary circle. So after that, after I make sure that my point is inside the sphere, I need to check if this point is inside the volume that I want, which is the volume of the cylinder. This is the second condition that I'm creating here with an if command. Here is only an if, because if the point lies between the cylinder, then it will sum a unitary number. It will score with 1 every time the point is inside the cylinder. It scores 1 point. Also, I calculate the variation of the volume, which is the square of the density. And with this manner, let me see. Yes, and now finish the if. In this manner, what we can do, when we finish the loop, which is right here in the last line, line number 30, we finish the 4 to nt. what I have to do is just evaluate the ratio between the points that are inside the cylinder over the total points on my sample, which is 1 million points. This ratio times the base volume of the sphere with unitary radius centered in the 0, 0 coordinates. So this is what I am writing here. The sum of volumes inside the cylinder divided by that total number of points, which is 1 million, and times the initial volume. Okay, so this will give me the volume of the Viviani's dome, and also a measurement of the error. This time I'm using the geometric means. Okay, so let me finish these brackets one moment. This one divided by nt, and I have to subtract the square of the later squared, let's to see, divided by nt, okay, times the same, yes, volume, and now the overall thing divided again by the total number of points, and then the square root, because it's the deviation of the, it's a standard error, in fact. And now, just finishing, what we need to do is print the overall the results. First, we will print the points inside the cylinder. No, the points inside the sphere, which is simple. These are the 1 million points, because we made sure with the loop while. Remember that. So all our points are 100% sure that are inside the sphere. So the total number of points inside the sphere will be these million points. Now we will see, this is the denominator of the ratio. Okay, now we will print, just copying the same, but now we will print the points inside the cylinder, which are counted by adding some volume plus density, remember? So these are stored in some volume, summation of the volume will be that. And yes, just to see the results on the screen. And now we will print the value of the volume, that is the intersection of the sphere and the cylinder, which is the Viviani's dome volume, in fact. This is just V, right? And let's finish. I'm using, well, from 7 digits for decimal parts. I'm printing a float number. Yes, and V is the result of this volume. And last but not least, we will printing. Hopefully, we will printing the error term of this volume. Let's modify here a little bit the source G. This is auto-correcting the number, and dv. Well, let's see what happens. Let's run this program just to make sure that it is going good. Let's name it and let's run it. And finally, let's run this program to see the results. The results will be 1 million points inside the sphere, a little bit more of 500,000 points inside the cylinder, and the volume is 0.6039 with an error of almost 0.0005 in this case.